right. Well, hello, students. I wanted to post a key for the second regression lab. Um, and the reason why is, of course, it's a bit more complicated because we've got not only do we have multiple independent variables, but also we are uh, doing a bit of iteration here. Okay. And so the goal is for us to develop a regression model that is, big fancy word here, parsimonious. Okay. The idea is that we want to develop a model which is as simple as possible, and yet does the best job of explaining variation in the dependent variable. And the reason for that is really one is more of a principle around simplicity, and the second is related to the first, which is the ability to articulate what the model means and translate it for management direction and management action. So what do I mean by all that? So in terms of parsimonious, what we're looking for is we're following the model that was developed centuries ago called Occam's razor. And I'm paraphrasing, but the idea of Occam's razor is the most simple explanation is usually the best. Okay. And other scholars have talked about this. In fact, Albert Einstein talks about if you can't explain something simply, then you really don't understand it, which is a very challenging statement for me, to hold yourself to that kind of standard. The second thing is, again, if I have a regression model with, let's say, 8 different independent variables, those 8 may do a really good job of explaining variation in the dependent variable. However, if I am an executive in an organization, it's a lot easier to explain an answer to, let's say, 500 employees that has only 2 or 3 key drivers or independent variables rather than 8 or 10. Okay. And that's just a recognition that people understand things, are more likely to remember and understand things if they're put in a simple fashion, maybe 1, 2, or 3 things that they would have to focus on rather than 7, 8, 9, 10. And you can think about lots of examples in that. If you're an athlete, you want to try to focus on 1 or 2 things at a time to try to improve rather than focusing on many different things. So with all of that preamble, let me go ahead and we'll work on this problem. So here we can see we've got, and I think this is actually like real data. At least at some level. So we've got all these different cereal brand names. I think we've got around 67 of them. And then we've got the manufacturer. And then what we're trying to do is we're trying to understand which of these 4 independent variables, sugars, sodium, carbs, and fiber, seem to be most explanatory in driving variation within the dependent variable, which is calories. Now, those of you that are super healthy and you understand nutrition, you may not even have to do this model. I mean, you need to do it for the class, but you may inherently already understand what the answer is. But nevertheless, so let's go to our data. There we go. We go to data analysis. Okay. And our little dialog box comes up. I'm going to select regression. And then we want to highlight our Y variable. So that is dependent variable, which is calories. Okay, so we've highlighted that. And then this may have been a little bit confusing for some, but we can throw all of these independent variables in the same field here, which is the X range. So we've got 4 different independent variables in this X range. We want to select labels, right? Because otherwise it gets confusing when we look at the regression output, which variable is which. We can select 95% confidence level. Let's go ahead and select the output range. We'll put it in this same worksheet, okay? And well, we can go ahead and do the line fit plots, okay? All right, so let's go ahead and run this. And that didn't take long. All right, so what have we learned here? Reel this in a bit. Okay, so what have we learned? Okay, so we have our R squared and adjusted R squared of 74 and 72 respectively. So that's good to know. All right. The other thing that, you know, of course, we've looked at, these coefficients are what we need in order to derive a model, okay? And then we've got our p-values, right? And so what we want to remember is that our alpha value is 0.05. So then what we're looking at is among these 4 independent variables, which of them are below 0.05. So sometimes this is a little tricky, but we can see here we've got 3.9 e to the negative 10 and then 5.7 e to the negative 16. So what we have to remember is those are really small numbers, okay? And sometimes it's confusing. So we have to remember our scientific notation and recognize that if we have e to a negative power, that means that that is a small number, okay? The other thing we notice is that carbs and fiber are greater than 0.05. So based upon what we see here, looking at all of the independent variables thrown in the same bucket together, we see that we're able to explain around 73% of the variation in the dependent variable, which is calories, by sugars and sodium. And it kind of makes sense, right? Kind of makes sense that sugars would contribute significantly to calories, and then sodium as well. Now, one of you mentioned last week this notion of multicollinearity. So I would suspect, and I'm not going to run the test on this, but there is a VIF, variance inflation factor, that I could run on these independent variables. And if I were I would guess that there would be collinearity between sugars and carbs, which kind of makes sense, right? Those are, in some ways, I'm not a biologist, but those seem to be related. So now we have a question, right? We've done our first regression. However, based upon what we've seen here with these p-values, that there's two of these, carbs and fiber, which according to their p-values are not significant drivers in the regression model. And therefore, we should look at iterating the model by removing carbs and fiber from the model and rerunning it. Okay, so let's call this model 1. All right, so let's go ahead and rerun it, except we are going to remove carbs and fiber. So I want to make sure I take those out. All right, so have this little dialog box here. So I'm going to remove those. Okay, so let's go ahead and rerun. Oops. Data analysis, regression. Okay, we don't have to change our y, that's staying the same, but we are going to change our x. So we're just going to focus on sugar and sodium. Okay, we still want the labels. We still want the confidence level. Let's change our output range. Okay, so we've got model 1 here. Let's put, actually, you know what? Let's put our model 2 beyond our line fit plots. Okay, so we'll put it there. I think I'm going to take the line fit plots out. Just it kind of clutters it up a little bit. Okay, I'm going to click OK. All right, so this is, we're going to call this, excuse me, model 2. All right, so we've got our R squared, adjusted R squared between 71 and 72. It's interesting, we can sort of compare to our 74 and 72. Pretty darn close, right? All right, so now let's look at our p-values. Well, as we would probably expect, the p-values for sugars and sodium are very small, e to the negative 13, e to the negative 18. Okay, so again, not really a surprise there. So now we have a managerial question. Okay, we've iterated twice, model 1, model 2, taking out carbs and fiber. We have reduced, if we just look at the adjusted R squared, we've reduced it from, let's say, if we round to the hundredths, 0.73 to 0.71. So the explanatory power has gone down to 1/100ths. So our question is, or a couple of questions. A, which model is better? So we have to define, and what does better mean? Well, which one is simpler, parsimonious, right? Occam's razor. And then 2, does a good job of, or just as good of a job as possible to explain variation in the dependent variable. So the question is, by reducing independent variables by half and only losing 2/100ths of a point, 2/100ths in adjusted R squared, is that a good trade-off? My answer would be yes, right? So you can imagine if you are a personal trainer that has uh, a nutrition background, formal training in nutrition education, then the idea would be if you're trying to help your clients get more fit, model one would say, hey, there's 4 things you can watch: sodium, sugars, carbs, and fiber. And if you reduce your intake of those, then your overall calorie intake is going to go down. So you can imagine if you're a client, it's like, okay, sugars, carbs, sodium, fiber. Holy cow, that's 4 things. Now I got to think about everything I eat and how much of those 4 is in stuff that I eat, right? It becomes complicated pretty quickly. On the other hand, if we say, again, if you're a personal trainer, you could say, well, there's lots of things that you should watch out for, but really the 2 things are sugars and sodium. Okay. So if you reduce sugar intake and you reduce your sodium intake, watching those 2, you're going to have some positive outcomes related to reducing your overall calorie intake, right? So that would be my recommendation. My recommendation would be to select model 2, and I would use that and offer that up as the optimal solution. Now, alternatively, some of you have had regressed each one of the independent variables individually against the dependent variable. And while that sounds maybe like a good idea, the problem with that is that while you can look at the isolated effects, you don't see the kind of the collinearity or the interaction between the independent variables amongst themselves. The other thing is it's just not realistic, right? It's not realistic. So the appropriate way to do it is to put all of the independent variables in the initial model and then examine the p-values and then throw out the ones that are insignificant based upon our confidence level and then rerun the model. Okay. So I hope that helps. I will post this right away in Discovery, and feel free to email me if you have any questions. Thank you very much.